Good morning. How are you, chemists? Are you doing well? Are you well rested after our whole week off from the lab? You guys ready to start up labs again this week? So remember, we're in lab again this week. We have our learning assessment first thing, so make sure you're on time for that. Then we will be doing our nitration lab, keeping up with our schedule. Next week we have our ACS exam, and so remember, you don't have to show up in person for that. That is going to be something where you can do that at home. It'll be a Blackboard exam, but it is our ACS exam. So just some notes about that. It is a closed book, closed note exam. It's the only exam we have where you have no notes this semester, so please abide by that rule. Closed book, closed notes, nothing, no sheets of paper, nothing other than some blank pieces of paper for scratch paper for that exam. It's going to be, you'll have 80 minutes, and I think it's 40 questions in 80 minutes. And a lot of the questions, I took it myself, a lot of the questions you can answer quickly. So as long as you know what you're doing, then you will be okay. So what should you study? Study everything that we're doing right now. So be preparing yourself for the final. Also, go back and review things from 351, especially the things that you're seeing over and over and over again. Acids, bases, nucleophile, electrophile, SN2, SN1, E1, E2, oxidation, reduction, all this stuff that we're seeing repeatedly, that stuff is going to for sure show up on the ACS exam. So the ACS exam is something that covers the entire school year of organic chemistry. So make sure you are studying for that, just as you would for the final exam. So it's nothing wasted. You're getting ready for the final. All right, so closed book, closed notes, 40 questions, 80 minutes. You'll do it during your lab time. So we'll start at 1:15 for the Thursday people, and then, or sorry, Wednesday, Thursday afternoon people, and then Thursday evening, I'll talk to you guys tomorrow night about what time you guys want to do your exam. But it'll be 50 points. So whoever gets the highest score, I'll probably get at a curve where the highest score ends up getting over 50, and then everyone else will get scores according to that. So I'll just adjust it based on, whoever does the best in class. But what was the last thing I needed to say to you about that? I don't remember. But anyway, so that's the beginning of your final exam, technically. So your final exam is out of 200 points, so that's 50 of those points on the ACS exam. So prepare as you would for the final, and you should be okay. Any questions on that?
Hold on, yeah, Professor. So the exam will exactly start at 1:15, or we have a time period where we can start it and
No, it'll probably, so I can talk to you about that in your lab section. So I'm fine with us starting it a little bit later for those who are in the afternoon, but we just have to come to a consensus with everyone in your lab. So we'll all start at the same time. And so along with that, remember, just like what we've discussed with the learning assessments, don't discuss it with other sections since they're taking it at a different time. So with the learning assessment that we're doing this week, with the ACS exam, don't discuss it with other sections until everyone has taken it. So, and then also with this, you really want to make sure you're being very careful because this is a national exam, and so we can get into a lot of trouble if we are breaking ACS's rules. So that's why I have to abide by these rules, no notes, closed book, etc. But yeah, we can discuss alternate start times, so we all will start in that section at the same time and have the same 80 minutes. But that'll be next week, so we don't have to show up to lab next week, and then we'll have 2 more weeks in lab, and then we'll be done. So we only have 3 more labs to do. We are so close to the end, you guys. You can do it. All right, let's get into our lecture. So this is something that trips up students very regularly. I'm warning you ahead of time. This concept trips up students, so pay very careful attention. Make sure you are paying attention to what I'm talking about here as we talk about hemiacetals and acetals. So we were just discussing what happens if we have a strong nucleophile with our carbonyl And so neutral, basic, neutral, basic, or acidic condition. So we're seeing things that can happen with our carbonyl in the presence of alcohol. So alcohol as a weak nucleophile. We know that it's a poor nucleophile, right? We've known that since last semester. So what can happen, so here are two different reactions, is we can start off with an aldehyde or with a ketone. It doesn't matter which one. But if we add one equivalent of alcohol, then what will happen is we'll form something called a hemiacetal. It's called a hemiacetal. It has an H, an OH on that carbon. So we're taking this carbonyl where we have 2 bonds to oxygen, and we're turning it into this hemiacetal carbon that still has 2 bonds to oxygen. We are not doing an oxidation here. What is oxidation? Gaining bonds to oxygen. We're not doing a reduction, losing bonds to oxygen. The carbon that has 2 bonds to oxygen still has 2 bonds to oxygen. Now let's look at R prime. That would be a carbon that's attached to an oxygen also. This one is 1 bond to oxygen. Where's R prime? It still has 1 bond to oxygen. Again, R prime, 1 bond to oxygen, that carbon, still that carbon has 1 bond to oxygen. We are not oxidizing. We are not losing or gaining bonds to oxygen as we do this reaction. Aldehyde plus alcohol yields hemiacetal. This is a reaction that is reversible. Equilibrium exists here. Equilibrium usually favors this side where we have the aldehyde or the ketone. So we rarely isolate the hemiacetal in real life. But remember that aldehydes are more reactive than ketones. And so it's a little bit easier for us to make the hemiacetal with the aldehyde than it is for us to make it with the ketone. Aldehydes are more reactive than ketones, so we can isolate the hemiacetal. We have a better chance of isolating it with the aldehyde hemiacetal than we do with the ketone. But notice what we have. So what's attached to this carbonyl? R and H. We still have R and H. And then we have 2 bonds to oxygen. Same with the ketone. R and R. We still have those 2 R groups attached to that carbon. So this is something that is very important because we can make these rings also. If we have an aldehyde or a ketone that has a hydroxy group, it has the alcohol elsewhere on the chain. We have both of those reactive functional groups, either an aldehyde or a ketone plus an alcohol. If they're both on the same ring, same chain, we can make a 5 or a 6-membered ring because we know that those are strain-free. So we're going to make a cyclic hemiacetal. A cyclic hemiacetal. These are more stable than acyclic hemiacetals. So we like to do these reactions. So you add in a little bit of acid, that'll help this reaction to go. Look at our equilibrium now. Equilibrium lies on the side of the formation of the cyclic hemiacetal because that's very stable. But we're reacting this oxygen here with this carbonyl. This carbon still has 2 bonds to oxygen. This carbon still has 1 bond to oxygen as we are doing the reaction. We are not changing the oxidation. So why do we care about this? Well, this is important in sugar or carbohydrate chemistry. In sugar or carbohydrate chemistry, most of the sugars prefer to form these 5 or 6-membered rings. So here's glucose. Glucose here, yeah, it's a straight chain. We have an aldehyde and we have many alcohols on it, but specifically this alcohol on carbon 5, that's the one that we care about. And so what happens is that the aldehyde form can cyclize to form this cyclic hemiacetal. Notice here that a trace amount of it is the aldehyde form, but the majority of it is in this cyclic hemiacetal form. This is how glucose exists. Glucose exists in this ring form. So if you've studied biochemistry, you know about this ring form. You know about your anomers, your alpha, beta anomer, etc. But this is what happens with these carbohydrates, with sugars. They actually exist in a ring form, but they can ring open to reform the aldehyde and alcohol. So they can close and reopen. This is mutarotation that is occurring. So what we said was that we have an aldehyde or a ketone plus one alcohol gave us a hemiacetal. But what happens if we use two equivalents? If we use two equivalents of alcohol, we go beyond the hemiacetal to the acetal in the presence of excess alcohol. And then we use some kind of an acid catalyst. We can turn our carbon, again, 2 bonds to oxygen. This is the same carbon. It still has 2 bonds to oxygen. It still has R and 2 bonds to oxygen. What about R prime? Well, R prime has 1 bond to oxygen. R prime, 1 bond to oxygen. R prime, again, 1 bond to oxygen. And you can see where both of those OR groups come in. Now, they tried to color code this. I'm going to change the color of this. This is really this. And so we lose water in the course of this reaction. So let's look at the mechanism. So the mechanism for the acetal formation has the hemiacetal in it. We form the hemiacetal, and then the hemiacetal goes forward to react to make the acetal. Notice that all of these steps are reversible. So we're going to just be going forward from our aldehyde or ketone. We know the aldehyde's more reactive, so they're starting with the aldehyde, but you could do this reaction with a ketone just as well. So what happens in our first step? Well, our oxygen, remember, that is basic, and so that goes and picks up a proton. And so when it picks up a proton, we end up with these 2 resonance forms that we can draw, where we make our carbon very electrophilic, because we get a full positive charge there, because oxygen is pulling away its electron toward itself. So that makes this very electrophilic, so we can use a poor nucleophile, like the alcohol, in order to attack that carbon. You know this reaction. So we attack that carbon, push the electrons up. We end up with this carbon that is a tetrahedral carbon instead of trigonal planar. And we have to lose a proton. So we get this oxonium ion. We know that that's very acidic. We know that this is an acidic proton, and so we can lose it. So what did we do? We added in a proton, then we regained it, right? It's catalytic acid. And so what we form here is our hemiacetal. We know it's hemiacetal because we have the OH. Hemiacetal has the OH attached. So then with our hemiacetal, we can go forward. So our hemiacetal, we have this oxygen, these 2 oxygens that, again, are kind of basic. And so we have some acid around. We can protonate the oxygen, giving us a good leaving group. We know this. Water is a good leaving group, oxygen with a positive charge. So when that leaves now, we make water as our leaving group, and we end up with this intermediate that can be stabilized by resonance, because we know oxygen is an electron donating group by resonance also. It can pull away electron density, or it can donate electron density in. So it donates electron density in to help stabilize the positive charge, but we still have a very electrophilic, carbon here, because it has a positive charge in one of our resonance forms. So again, we can use a poor nucleophile. Now, what did we say? We're going to use 1 equivalent to make a hemiacetal, 1 equivalent of alcohol to make a hemiacetal. Here's a second equivalent here. That second equivalent helps us to make the acetal. So we use our poor nucleophile, it attacks that carbon. Our last step is we have this proton here, it's still there, it's very acidic. We know this reaction, lose the proton, regenerate our acid catalyst, and now we have our acetal, where we have still a carbon with 2 bonds of oxygen, but now those are both ethers. They're both ethers on that carbon. Each step is reversible here. So when we're doing this reaction, we have to think about, okay, this is a reversible reaction. How do we push the reaction forward? How do we, if we didn't want the reaction to go forward, what would happen? So we know that with Le Chatelier's principle, if we add, it shifts the equilibrium away, right? Add a reagent, shifts the equilibrium away. Add shifts away. And so if we have excess, that means we're adding alcohol. So that's going to shift the equilibrium forward to formation of the product. If we are removing, that's going to shift the equilibrium to that side also. So we might want to remove water as we are forming it as well. And so this is something that'll help us push our equilibrium forward. If we remove water as it gets formed, we put things in there that can absorb water, that'll also shift the equilibrium forward to formation of products. If we have a lot of water around though, that'll push the equilibrium the other direction. Then the other thing that we can think about is, okay, what do we need to go backwards? When we form our acetal, the first step is protonation, right? So if we go back and reprotonate, that's going to hydrolyze our acetal. Acetal hydrolysis, that means going the opposite direction, the reverse reaction. So how can we inhibit that? How can we slow down the reverse reaction? If we neutralize the acid catalyst. So we neutralize this, then we can't go back. So in the end of the reaction, we always have a neutralization step where then once we neutralize it, we can get the acetal. If we leave it and we let it sit with the acid around, then it'll equilibrate and it can go back and forth at that point. So you need the acid around but to start the reaction, but then you want to remove it at the end of the reaction. Questions there? All right, so with the acetals, we can use them as protecting groups. So we've talked about protecting groups before. Remember what they are. They are groups that will be used to mask or protect, to kind of hide reactive groups. And a protecting group hides a reactive group so you can do a different reaction. So how do we protect carbonyls? Remember, carbonyls are very reactive. We convert them into acetals. So acetal is an ether-like compound, right? We have these two alkoxy groups, these two ether groups. Instead of it being very electrophilic, this carbon, which is very electrophilic, now this isn't very reactive. Ethers are very unreactive. So we turn our carbonyl into an acetal, and then we can remove it later, right? We know this is a reversible reaction, so it has to be reversible so that we can protect the group when we want it to not react, and then remove it when we want to make it back into the carbonyl. So a protecting group allows for selective reactions. We have two or more reactive regions. We want to protect one, turn it into unreactive, do the reaction when we want it to be, and then remove the protecting group later. So let's look at a protecting group that gets used. This is very popular, using this diol. So here we have these two carbons, and both of them have an OH on them. So with this, we said we needed two equivalents of alcohol, right? Two equivalents of alcohol in order to make the acetal. If we use a diol, we can make a cyclic acetal. So again, this carbon that's blue, they're showing you it, 2 bonds of oxygen, still 2 bonds of oxygen. But now those two oxygens are bonded to these two carbons here, and so we make this cyclic acetal. This reaction is very popular because it reacts quickly and easily, but also because we have two starting materials making two products. So the two starting materials, 1, 2, and then the two products, 1, so water, and our cyclic acetal. What would happen usually? Usually you would have, let's say, some kind of an aldehyde or ketone, and then you would have an alcohol and another alcohol. And yes, that would form water and the acetal. So we would be taking 3 starting materials and turning them into 2 products. This isn't very favorable based on entropy. It's more favorable to have 2 going to 2. And so this is a more favorable reaction here based on entropy. So this is how we do it. And you know that you can reverse this reaction also by having some acid around. It goes the opposite direction. So let's look at why we would do this. All right, so we have this starting material here, this 3-iodopropanol. So I'll show you what could happen with this reagent. So if we added in this reagent here, 1-hexynyl lithium, then what would happen? We have 2 reacting groups, right? We have here a partial positive, partial negative there, and we have a partial positive, partial negative here. We have 2 carbons that are electrophilic. What would it prefer to do? Which one is more electrophilic? The more electrophilic atom is actually carbon 1. And so that would be the reaction that would occur. And so we'd end up with this product where now we have an alcohol here, so carbon 3, carbon 2, carbon 1, and then we're bonded to carbon 4, 5, 6, 7, 8, and 9. This would be our product there. So 2-step process, 1 and then 2. But what if we don't want this product? What if we actually want this product here? What if we want 4-nonylal? We can't go through that same process because carbon 1 is a better electrophile than carbon 3. So starting off with the exact same reagent, so the 3-iodopropanol, but then we protect it. So we add in our diol, we make the cyclic acetal. And so then with our cyclic acetal, now carbon 1 isn't reactive. Now carbon 3 is our best electrophile around. We've hidden carbon 1 because we've turned it into an acetal. So now we can do this SN2 reaction where now carbon 3 reacts. So we're making a bond between carbon 3 and carbon 4. That's the bond that we're making. And so when we make that bond now, we still have our acetal. We add in some acid and water, aqueous workup step. It removes the acetal. We regenerate our original aldehyde. So we can protect the carbonyl and then we deprotect it later. Questions on this? All right, so that's our acetals and hemiacetals. Let's move on to 17-12. So we skipped 17-9 to 11. But that's good stuff, so read it. It's good for your future, but we're just going to cover here 17-12. So here we have another name reaction. This is called the Wittig reaction. Wittig, this is a German. And so with this, we have this thing called a phosphorus ylide. What is a phosphorus ylide? This is a phosphorus ylide. And so here we want to talk about how to make a phosphorus ylide. We use this in the Vidig reaction, but right now we're talking about how to make this reagent where we have a negative charge on the carbon, a positive charge on the phosphorus. So we make this ylide by using triphenylphosphine. Triphenylphosphine is this. These are the same thing. So phosphorus, lone pair, 3 benzene rings around it. Phenyl, remember, for benzene ring. Triphenylphosphine. So triphenylphosphine reacts with some kind of a haloalkane in an SN2 reaction. So this is our nucleophile. Our carbon is our electrophile. Leaving group leaves. We make a carbon-phosphorus bond. Phosphorus has a positive charge, but remember, our carbon needs to get a negative charge. So this is only step 1. This is our first step in how to make the ylide. That's what we're talking about here. How to make the ylide. We're not doing the Wittig reaction yet. This is just our first step. We make this phosphonium salt, which is our intermediate. Then we take that phosphonium salt that we just made, and we react it with some kind of a base. So alkoxide, sodium hydride, and butyllithium. Some kind of a base is used. It will deprotonate that proton that's on the carbon. And so we end up with a carbon with a lone pair with a full negative charge. And then that negative charge gets stabilized by resonance. We could delocalize that charge. And so because that carbon with a negative charge is right beside a phosphorus with a positive charge, makes it very stable, we end up with a neutral carbon, neutral phosphorus. If you look at phosphorus, remember that this can have an expanded valence shell. Remember, phosphorus can have more than 8 electrons around it. And so if you count that up, it has 5 bonds to it. And that's fine for phosphorus, but it's not okay for carbon. So we have made our ylide. This is our step 2 in making the ylide. This is what we use in our Wittig reaction. So I showed you 2 steps in how to make the ylide. Now let's see how we use the ylide. So we make our ylide, and then we can use it. Remember, this is stabilized by resonance, but we can use it in our Wittig reaction. So the Wittig reaction, we start off with either an aldehyde or a ketone and the ylide. And we put those 2 together where if this is our carbon 1, this is our carbon 2, those 2 carbons end up bonded to each other in a double bond to one another. And then phosphorus and oxygen, those 2 end up in a double bond to one another, giving us triphenylphosphine oxide. We always make triphenylphosphine oxide, and then we make some kind of an alkene in our Wittig reaction. So our Wittig reaction is really nice because we make only one alkene product. Think back to what we did with the eliminations. In our eliminations, we could have a mixture, a wide range of products. Depending on if it's E1 or E2, we could get a wide range of products. But with a Wittig, only one product is possible. All right, so notice what the solvent is, diethyl ether here. But we have our Wittig, so 1, 2, 3, 4, an aldehyde, reacting with our ylide. We'll call this 5, 6, 7, and 8. And so in this product, carbon 1 is now bonded to carbon 6 in a double bond. Where we had a double bond to oxygen, a double bond to phosphorus, now we have a double bond to carbon. So we make this alkene. And then we also make our triphenylphosphine oxide. So this is what we make there. They're just not really showing you it, but you also make that. Here we use a ketone, so we number it from either N Carbon 3 is now bonded to carbon 6. We only make this one product and the triphenylphosphine, only one product formed. But remember our elimination reaction? Remember for the E2 reaction? So here we're doing the E2. And so remember for the E2, we had two different types of hydrogens, right? Here we have these hydrogens, and then we can go one carbon away. These are the same as these, right? Those two are the same, ethyl on either side, so it doesn't matter which one. If we deprotonated one of those ethyl CH2 hydrogens, we would get this product, versus if we deprotonated that methyl, we would get that product. So we get a mixture of isomers here. Whereas, look, these are the same products, but we only get one isomer if we're doing the Wittig. If we're doing the elimination with this starting material here, then we can get a mixture of products because those two hydrogens can both react. And we know that this would actually probably be minor, right? And this would be our major product, depending on what the base is. Let's say it's an unhindered base. But if we want to make all of only that one product, that's the minor product, the Wittig reaction is the way to go. Questions before we move on to the mechanism? All right, so looking at our mechanism, we have our ylid. We know that one of our resonance forms of the ylid has that carbon with the negative charge, phosphorus with the positive charge. So they're showing you the mechanism from that. We use our carbon here as a nucleophile. We use this carbon as an electrophile. And so nucleophile attacks the electrophile, move electrons up to the oxygen. We end up with our oxygen with a negative charge near our phosphorus with a positive charge. This is called a betaine or a Zwitter ion, meaning that we have these two charges. So think about like a amino acid. That's a Zwitter ion. It has a positive and a negative charge on one molecule, but it's overall neutral. So because we have this nitrogen that is nucleophilic and a phosphorus that's electrophilic, we can attack the phosphorus, giving us here this four-membered ring. So here, oxophospho, phosphocyclobutane. So we get this four-membered ring. With the four-membered ring, you know that is strained. And so we can easily open that ring. And as we open it, we get a double bond between the two carbons, and we get a double bond between phosphorus and oxygen. Those are going to be our lower energy bonds. This bond here is very strong. And so that's going to drive the reaction forward. This triphenylphosphine oxide, double bond to oxygen, that's going to push the reaction forward. So that's our mechanism. Make sure you know the mechanism for the Wittig. But with this is a nice reaction because we can conduct it in the presence of other things that might be reactive. We want the carbonyl to react, but we can have other groups around, ether, ester, halogen, alkenes, alkynes. They can all be around, and so this will tolerate various functional groups. That's what we say in organic chemistry. It tolerates various functional groups. So with our ylid, it matters if it's a conjugated or non-conjugated ylid for the stereochemistry of the alkene that we make in the end. If we have non-conjugated ylid and aldehyde, then we're going to make the cis or Z alkene. So look, there's no conjugation. We only have this one double bond. And same with this. There's no conjugation there in our aldehyde using THF, so ether or THF for the solvent, but we get our cis product. So 6-to-1 cis to trans there. Even though we know trans is more stable, it prefers to make this cis alkene. But if we have a conjugated ylid, now it's going to favor the formation of the trans product. So trans or E product. So here's the synthesis of vitamin A that this German chemical company uses in order to, they have this Vidig reaction in their synthesis. So they start off with the intermediate, right? This is after step 1. We get this salt, and then this is our step 2 where we make the ylid. So in our step 2, they added base, they added in methoxide base to deprotonate, furnishing the ylide. Notice that the ylide is conjugated, double, single, double, single, double. Notice that our aldehyde is also conjugated. Double bond here, single bond, double bond. That is conjugation. It doesn't have to be carbon-carbon double bond, carbon-oxygen double bond, or carbon-phosphorus double bond. Same, conjugated double bonds. That leads to the formation of this green bond here, which is the trans product. So I call this 1, 2, 3. I call this 4, 5, and 6. You can see that carbon 1 ends up bonded to carbon 4. We maintain the stereochemistry throughout, but then this new bond that we're making between 1 and 4, it's a double bond. So then all they do is what's called an ester hydrolysis. We have an ester functional group here. We hydrolyze that with some base and some water. We end up with this alcohol. This whole product is vitamin A1. Questions on that? All right, moving on to our last section. So we skipped 1713 and we're into 1714, talking about aldehyde ketone oxidations. So this is review. You should know this already. A primary alcohol in the presence of some kind of a strong oxidizing agent. What would that be? Well, that could be our sodium dichromate. That could be our, potassium dichromate. That could be our CrO3. And then we would have, so I guess I should say slash, and then we'd have H2O, H2SO4. Also, PCC could be used here to take the primary alcohol, turn it into aldehyde. But if we have a strong oxidizing agent around, like our dichromate reagents, because we have water and acid around, we're going to go forward to the carboxylic acid. And so we know if we use one of these reagents, we get the carboxylic acid. Review stuff. What about with the secondary alcohol? Well, with the secondary alcohol, as we oxidize it, going from 1 bond to oxygen to 2 to now 3 here. What's happening with the secondary alcohol? Well, we're going from, again, 1 bond to oxygen, but it's a secondary alcohol. Here we form ketone, 2 bonds to oxygen. We can't keep going forward to 3 bonds to oxygen because we have these 2 carbons here, and we can't lose carbons. All we can do is lose hydrogens. So if we keep oxidizing, nothing will happen. We stop at the ketone if we start off with a secondary alcohol. And then remember, a tertiary alcohol cannot be oxidized at all. This is review. This is what you should be studying for our ACS exam, and you should just have this in your mind in general. So these are strong oxidizing agents. Well, what happens if we have a mild oxidizing agent? A mild oxidizing agent will allow for us to oxidize only the aldehyde in the presence of other functional groups prone to oxidation, like alcohols. With a mild oxidizing agent, this will not oxidize alcohols. A mild oxidizing agent will only oxidize aldehydes. So here we have, because aldehydes are very reactive, so here we have something called Tollin's test. And so with Tollin's test, this helps us to distinguish if we were doing our unknowns, this would be a test that we could do. And in reality, you don't do it. It's a dangerous test for undergrads to do, but it is a test that could be used to figure out what your unknown is, what functional group you have. So this helps you to distinguish between aldehydes and ketones or other functional groups. So you have an alcohol there or something else. Only the aldehyde will react. Tollin's reagent, which is silver nitrate and ammonia, only will oxidize the aldehyde, not ketone, not alcohol. So here we have an aldehyde, and we add in our Tollens reagent, which will be silver ion, Ag plus. And so when we do this, it's a mild oxidation, but we end up with the carboxylic acid. So here, this is ethanoic acid, and then we make a silver mirror. We make solid silver, silver metal. So what's happening here? Well, in this reaction, we're taking the aldehyde and we are oxidizing it to the carboxylic acid. But as we do an oxidation, there's always some kind of a reduction with it. And so Ag plus is getting reduced. So I should put a 2 here. 2 Ag plus 2 electrons. That's going to form Ag, but it's 0. So this is the ion, and this is metal. This is a reduction, right? A gain of electrons. This is a reduction. So as we do this oxidation of the aldehyde to the carboxylic acid, we're doing a reduction of the silver ion to silver metal, and that gives us the silver mirror. The silver mirror. It actually plates this silver on the outside of whatever, on the glass of whatever you do this reaction in. So let's look at this reaction. Give me a second.
Using Tollens reagent to test for aldehydes. The silver mirror test. This video demonstrates how to use Tollens reagent to test for aldehydes. This video first demonstrates the preparation of Tollens reagent. Two tests will then be carried out. One shows a positive result, and the other shows a negative result. Preparation of Tollens reagent. Add 2 ml of 0.3 molar silver nitrate solution into a clean test tube. And then add 1 to 2 drops of 0.3 molar sodium hydroxide solution. Brownish precipitate of silver oxide will be formed. Add a 3 molar aqueous ammonia solution drop by drop with a dropper, until all the silver oxide precipitate is just dissolved. Do not add excess amount of the ammonia solution. The solution obtained is aqueous diamine silver solution, which is also known as Tollens reagent. Add a small amount of sample to the Tollens reagent. Shake the mixture gently, and then stand it on the bench for 10 minutes. Observe if there is a silver coating formed on the inner surface of the test tube. If there is no observable change, warm the mixture in a warm water bath for 5 minutes. If the sample is an aldehyde, a positive test result will be obtained. If the sample is not an aldehyde, the test will give a negative result. It is important that Tollens reagent.
All right. So you could see that with the aldehyde present, there was that silver mirror. And so that glassware, that's it, that's done. That has that silver coating on it for the rest of time. But for the, if it's some other functional group like a ketone or an alcohol, it will not react. So that's our Tollens test. And so this is a process that can be used to make mirrors, actually. So they used to do this. I'm not sure if they still do this and for every single mirror, but it is possible to do this silver mirror, this Tollens reaction, in order to put that silver coating that is a mirror. Then we have Benedict's test. So Benedict's test also helps us to distinguish between, sorry, this is messing up here. Benedict's test helps us to also distinguish between aldehydes and ketones, but now specifically it has to be an aldehyde with an adjacent hydroxy group. So Benedict's is going to be used for, give us a positive test result when we have a hydroxy beside the aldehyde. Hydroxy beside the aldehyde. Benedict's beside. So what is our Benedict solution? This is copper 2 sulfate. Again, the copper 2 gets reduced as the aldehyde gets oxidized. So we're still doing an oxidation with a reduction. We're not breaking that rule. But our copper has this nice blue, bright blue color when it is the ion form. And then when it gets with the oxygen, when it gets oxidized, it turns into copper 2 oxide, which now is this brick red solid. And so, you know, if you added in an aldehyde with a hydroxy beside, you're going to make this brick red solid because it's going to form this copper 2 oxide, and then you'll also form the carboxylic acid. Notice that you have to have a hydroxy group beside, so we can say, remember we talked about our alpha carbon, right? Alpha carbon is the carbon right beside. There has to be an alpha hydroxy group. And so with that alpha hydroxy group, the hydroxy group doesn't react. It doesn't get oxidized. With a strong oxidizing agent, yeah, that would react. But with a mild oxidizing agent, it doesn't. Benedict's test is similar to a different test in the textbook. It's similar to Fehling's test. Those are the same thing. So why do we care about Benedict's test? Well, again, back to the sugars. Sugars are aldehydes with alpha hydroxy groups. So here we have glucose. It's an aldehyde with an alpha hydroxy group. And so with this, we take our copper 2 plus and turn it into copper 1 oxide, just like before, our copper 1 oxide brick red product. But with our glucose, we turn our glucose into gluconic acid, where the aldehyde got converted into the carboxylic acid. So if you want to test a patient to see if they have glucose in their blood or urine, it's quick to just do Benedict's test. And so in a hospital, sometimes they will just do a quick Benedict's test. If they get this brick red solid, they know, okay, yep, this patient has possibly has diabetes, where there is glucose in their blood and urine rather than getting into their cells like it needs to. So we can use Benedict's test for any kind of an aldehyde with a hydroxy beside, especially a sugar or a carbohydrate. But remember, it's mild, so the alcohols won't react. Questions on this? Benedict's or Tollens test? All right, so we are to the end of this chapter. So lots of reactions that we know how to do. Let's get into the NMR IR problem. So get out your sheet. Have that right beside you. So first, let's start off with the degree of unsaturation, right? Our degree of unsaturation is where we always start now. So 2 times the number of carbons plus nitrogen minus hydrogen minus X, always plus 2, all over 2. So 2 times 8. We don't have any nitrogens, but we do have 8 hydrogens, no halogens, so plus 2 over 2, and so we get 5. What is that? Rings and or pi bonds. So now let's look at our IR. So IR, the first thing that we see is this 708 and 796. 708 and 796, those two together will tell us something. 708 and 796, let's see where they fit. 708, 796, no, it can't be in here. 708, 796, it can fit in here, right? Both of those numbers fit in those two ranges. So that means we have a meta-disubstituted benzene ring. Those two numbers together tell us that. All right, now we have 1580 and 1660. So this is where we're going to have to do kind of some like workarounds. We're going to have to like try something, maybe fail at it. It might not be always totally clear. So we have 1580 and we have 1660. They're in kind of the same region. So 1580, if we look at our sheet here, 1580, 1660, they both fall into this region where there's a benzene ring. We know there needs to be a benzene ring. So right now, let's just say 1580 or 1660 benzene ring. Then let's move on and we'll go back and figure out more about that. 2960, we don't need to look that up. We know that that's alkane. 3030, again, benzene ring with a hydrogen on it. So benzene ring with a hydrogen on it. We know there has to be a hydrogen for it to be meta-disubstituted. Then we have 3270. So 3270, we have two choices there for 3270. Look at your sheet. It could be a carboxylic acid, or could it be an amine? No, it can't be an amine, right? There's no nitrogen there. But it could be a carboxylic acid. Let me draw it. So we could have a carboxylic acid, or we can have an alcohol. So remember, we still have to figure out what this other one is. We have two things here. One is one thing, one is the other. So as we look at this, can this be a carboxylic acid? Well, what would we have to have for it to be a carboxylic acid? We would also need a peak in the carboxylic acid region. We would need the carbonyl of the carboxylic acid. This is the OH of the carboxylic acid here. But if we're talking about the carbonyl of the carboxylic acid, look at your sheet. That would be somewhere between 1710 and 1760. We don't have a number there in that region, right? There's nothing there. And so if it's not that part of the carboxylic acid, that means this isn't a carboxylic acid. That means this has to be an alcohol. So one of our oxygens is an alcohol, but we have two oxygens. The other thing has to be either 1580 or 1660, and there has to be an oxygen involved there. So 1580, 1660, if we look at this, 1580, 1660, it doesn't really fall into any of the regions, but it's close to 1660. And so let's say 1660 is either a ketone or an aldehyde. So 1660 is not this. This one is 1580. Now, how can I say this is true? We know that an aldehyde or ketone should be in the range of 1690 to 1750 wave numbers. So why am I saying 1660 is it? Well, for something that is in conjugation, when it is conjugated, when the aldehyde or ketone is conjugated, then it can be 30 to 40 wave numbers lower. Due to conjugation. And so that fits 1660, 30 to 40 lower based on conjugation. And so that makes sense here for this being an aldehyde that's in conjugation, probably with our benzene ring. So this is going to be an aldehyde or a ketone where we have, so I'll just call it R, where we probably have it directly attached to our benzene ring. And so you can see double, single, double, single, double, single, double. From the double bond here, double, single, double, and going all the way around. It is in conjugation. Questions on this? All right, so let's look at our degree of unsaturation. 5 rings or pi bonds. If we have some kind of a benzene ring, we know that that equals 4 unsaturations. And then either an aldehyde or a ketone, I'll just call it R, we know that that equals 1 unsaturation. So we have 5 unsaturations there. So this is as expected. Questions there? All right, that's where we'll stop. We'll keep going with this because the NMR stuff is pretty involved. So I kind of want to start it all up at one time. So you can work ahead though, work ahead on all these problems so that you are more so checking your work rather than trying to copy down what I'm doing as we do the learning checks. So make sure you've done them before we come back together. Remember, this is our last class this week. We do have lab, but this is our last lecture. So I won't see you again until Wednesday morning or our next lecture. So we'll pick this up Wednesday morning. And then remember, everything moves pretty fast in the last few weeks. So make sure you're paying attention to what is due when we have exams, etc., to help you out. Okay? All right, you guys, have a great day. And I will see you guys for your learning assessment today and tomorrow and for lab. Love you guys. Bye.
Quick question, Professor.
Oh, yeah.
Yeah. So like regarding